Hi, my name is Aziz, and in this particular presentation, I'll present some joint work with Florian Brandl from University of Bonn. The topic of this particular presentation is the general approach for probabilistic economic design with constraints. And in particular, I'll present a new and a very general rule called the Vigilant Eating Rule that we have devised. And this particular rule, it's not only applicable for various allocation problems, but it's also applicable for various collective decision-making problems in which agents have ordinal preferences over social outcomes. So our motivating example is that of allocating objects to agents, and this comes up whether you're allocating kidneys to patients, jobs to applicants, or positions to students. And the theory of matching market design and allocation received wide acknowledgement when Al Roth and Lloyd Shapley, they received the Economics Prize in memory of Alfred Nobel in 2012. And more widely, this issue of matching two sides to each other comes up in matching theory and discrete mathematics. But the ingredient that we consider in matching market design or matching under preferences is that at least one side, the side involving agents, has preferences over the other side. The moment you have preferences in a social choice setting, then a few mathematical economics criteria become quite prominent. Ideally, you want an outcome or a matching in which is Pareto optimal. Secondly, since agents' preferences are taken into account, then fairness criteria also come into the to consideration as well. And finally, strategic issues are important as well. For example, you might want to have an algorithm which is strategy proof, which does not incentivize agents to misreport their preferences. So the two angles that we take in this particular project are that we are focusing on allocation with constraints, and we are especially focusing on randomization. Our first observation is that many real-life problems, they have certain feasibility constraints, which could be physical, they could be based on diversity, or they could simply be capturing individual rationality requirements. Secondly, we want to pursue randomization, which is essential for achieving various fairness properties. And also, mathematically speaking, random allocations or random outcomes, they capture time-sharing arrangements. For example, it may be the case that a doctor is not matched to a particular hospital throughout. It's the case that a doctor spends 2/3 of her time in one hospital and spends 1/3 of her time in another hospital. So both randomization and constraints have deep roots in the economics literature. One particular paper that I'd like to highlight here is that of Bogomolai and Mola, which will feature in our next few slides. So just to be on the same page, let me just motivate why we're considering randomization. So this is a very simple example where two agents have identical preferences over two items, O1 and O2. And obviously, since both agents have identical preferences over these objects, it makes sense from a fairness point of view that both agents should have equal probability of getting each of these items. Now, if we expand this kind of example to more agents and various preferences, how do you allocate these objects to agents is an important question. And one particular rule that came up in the literature is that of Bogomolai and Mola, which is called the probabilistic serial rule, also referred to simply as the eating algorithm. And the reason why it's referred to as the eating algorithm is because it simulates an eating process in which all agents simultaneously eat their most preferred object until it's consumed, and then they move on to the next most preferred object. And this process continues until each agent gets exactly one item. So in this case, since agent 1 ate 3/4 of O1, for that reason, the probability of allocating O1 to agent 1 is going to be 3/4, which is reflected in the matrix at the bottom of this page. Now, when Bogomolai and Mola presented their probabilistic serial rule, they showed that when you think of preferences from the point of view of first order stochastic dominance, which is abbreviated as SD, then the probabilistic serial rule, it satisfies both efficiency and entry fairness with respect to SD. On the other hand, it was highlighted by these authors that random priority, which is a very standard and widely applied rule, it violates both of these properties. So because of these superior fairness and efficiency properties, various theoretical investigations have happened with respect to probabilistic serial, various characterizations have been presented, and there's a lot of work on researchers extending the ideas behind probabilistic serial to more general domains. For example, multi-unit demands, weak preferences, and so on. So our contributions in this paper are that we take inspiration from probabilistic serial, which is only applied for a very particular domain for allocations. We present a very general probabilistic allocation rule, which is called the Vigilant Eating Rule, abbreviated as VER, that applies to any closed set of feasibility constraints. We show that VER satisfies desirable efficiency and fairness properties, and then we show that VER, it leads to compelling rules for stable matchings under object priorities, where not only do agents have preferences over objects, but objects also have priorities over agents. In that case, what we show is that if both sides have strict preferences and strict priorities, then our VER rule, it's equivalent to deferred acceptance. And if the objects have no priorities over agents and there are no feasibility constraints, then VER coincides with the standard probabilistic serial rule. So already we've shown, or I've commented, that VER simultaneously generalizes two very well-known rules. In fact, I'll show how VER generalizes many other rules in the literature as well. This rule is especially useful for weak preferences, which arise in various practical applications as well. So the three key ideas which are our starting point for VER are directly inspired by some of the work, prior work on probabilistic serial and its extensions. The first idea is that we gradually enforce more and more constraints on the implicit working set of allocations. Secondly, in order to handle indifferences, it's not the case that an agent tries to eat the most preferred object. What we do is an agent tries to increase the probability weight of her most preferred equivalence loss, in which there are ties between all outcomes in that equivalence loss. Thirdly, just like in the eating algorithm, the consumption is irrevocable. So a lower bound of an agent for an equivalence loss can only increase, it cannot decrease. Now, if we apply all of these three ideas naively, what we see is that it does not immediately work, especially when you have complex feasibility constraints. So I'll mention a couple of challenges that arise. The first challenge that happens is that when agents are eating objects, the partial allocation may not violate any constraint at that point, but just because we have made some local decisions, it may cause an infeasibility in the future. So the solution to this particular challenge is that we always look into the future and take a very vigilant eating approach will be making decisions. So we let an agent eat an object or increase the probability weight of an equivalence loss only if the resulting partial allocation can be extended to a complete allocation. So this vigilant approach is adopted throughout the course of the algorithm. Now, another challenge that arises is a bit more intricate, and that is that it could be the case that an agent I can eat an object O, and it doesn't cause any infeasibility either in the present or in the future. And it's the same case for agent J, but it could be the case that if agent I and J both simultaneously eat object O, it causes some infeasibility either in the future or even in the present. In order to cater for this particular problem, our solution is that we maintain an active set of agents and we have an ordering over this active set of agents. And what we do is for each of these active agent, we identify the most preferred designated objects or equivalence laws that they can consume more, given that the previous active agents in that order can simultaneously consume more of the designated object as well. Note that it's very important that we don't specify by how much the previous agents need to increase their guarantees. The only requirement we keep is that it should be strictly more than 0. So by doing so, what we do is all agents who cannot consume more while allowing previous active agents to consume more are simply made inactive. And what we do is we try to do this eating process only for the set of active agents. For these active agents, we sort of simulate a vigilant eating process, which can be captured by this optimization program, which also takes into account the feasibility issues by looking into the future. So I'll walk you through, or in fact, just give you a slight glimpse of the pseudocode that I have for the algorithm. Basically, it's we're trying to maintain a set of active agents, which is mentioned in line 2. In line 4, we start a while loop, and this while loop continues until the set of active agents is empty. In this while loop, what we do is for each agent I, in line 6, we define its corresponding designated equivalence loss. And this is that particular equivalence loss for which it can increase the probability weight while allowing for all previous active agents to also increase their own designated equivalence loss weight by at least a little bit. So once we've identified these designated equivalence losses and we've identified the active agents, then we can run this optimization program, which is mentioned in line 13. And this process continues, this while loop continues until none of the agents are active. And at that point, a lot of constraints have been set or they're tight. And at that point, we simply find an allocation which is consistent with the feasibility constraint that we have imposed. So this is the end of the algorithm. Just to give you a very brief glimpse, the three main properties that we prove for this particular rule, or the vigilant eating rule, are that for every closed set of allocations, VR terminates and gives a feasible allocation. So we allow any kind of feasibility constraints as long as the set of allocations is a closed set. Secondly, when VR is applied to any closed set of allocations, it returns an allocation that is constrained SD efficient among the allocations in set X. Thirdly, in terms of computation, if X is a finite union of polytopes, then the outcome of VR can be computed in polynomial time, number of inequalities used to describe the set X. We also establish some very general fairness properties of the VR rule. In particular, we show that for any pair of agents, if that pair of agents satisfy, if the X set satisfies symmetry and convexity with respect to these pairs of agents, and if these agents I and J have the same preferences, then equal treatment of equals is satisfied with respect to these two agents. In other words, the allocation of agent I and allocation of agent J is exactly the same. Secondly, we show that if we move from closed set of allocations to the convex set of outcomes, in that case, VR satisfies what is known as an ordinal egalitarian outcome, which is a very nice ordinal concept that was proposed by Bogomolai in 2018. So apart from establishing some general properties of VR, we apply VR as a case study to an allocation problem setting in which not only do agents have preferences over objects, but objects or items also have priorities over agents. And what we find out is that we obtain new and desirable concrete rules or algorithms for this two-sided matching problem. So just to make sure that we're on the same page, now we're considering a setting in which agents have preferences over objects as before, but objects also have priorities over the agents. This kind of setting is very well established. In particular, if you've come across stable matching algorithms, then it's very well established that a stable matching exists in this context. And such a stable matching can be found by the deferred acceptance Gale-Shapley algorithm, which is not only finding an outcome which is stable, it's also constrained, Pareto optimal, and the algorithm is strategy proof. However, this deferred acceptance algorithm is not the end of the story, because a few challenges arise when you have weak priorities. In that case, we don't know how to achieve fairness, stability, and efficiency completely. How do we deal with time sharing? That is not captured by deferred acceptance because it just gives you a discrete matching. How do we incorporate additional feasibility constraints? And finally, most of the work is on agents having strict preferences over the other side. On the other hand, we try to deal with weak preferences as well. So stability is a very well-established concept in the context of stable matching problems, but obviously since we are considering probabilistic outcomes, we need to define suitable stability concepts which also apply to probabilistic context. And in this context, I just mentioned a survey which we wrote with Bettina Klaus in Social Choice in Wilford 2019, where we formalized and studied the relations between 4 different probabilistic stability concepts, in particular ex-ante stability, ex-post stability, fraction stability, and KMI stability. I won't go into detail about the specifications of these particular stability concepts. The main idea is that all of these are meaningful stability concepts in the context of probabilistic allocations, and they all coincide with this classical stability concept when you only consider the set of deterministic integral allocations. So these are some slides for the definitions of stability concepts in the probabilistic sense. I won't go into the detail. The main idea is that all of these are meaningful stability concepts for probabilistic context. So our main idea is that we treat this stability concept, a generic stability concept S, as a set of feasibility constraints, and then we can apply the VER algorithm. So SVER is an algorithm which is achieved by applying VER with respect to the set of feasibility constraints S, where the set of feasibility constraints S corresponds to the stability concept S, which could be one of the 4 stability concepts that are in the previous slides. So each of these SVER gives rise to a new algorithm corresponding to each of these stability concepts S. And what we prove is that SVER for each of these 4 stability concepts, it coincides with the agent proposing deferred acceptance algorithm as long as agents have strict preferences and the objects have strict priorities. We also show that this algorithm, obviously, since it always returns, we are implementing VER with respect to feasibility constraints S. It obviously satisfies S stability. It also satisfies S constraint SD efficiency, which follows from our more general results. And also, equal treatment of equals also follows from our more general results. On the other hand, a very weak version of strategy proofness, a very weak version of NV freeness, and also global SD efficiency are not satisfied by this algorithm or this class of algorithms. And this is not really a design flaw of the algorithm, because we present 3 fundamental incompatibility results which show incompatibility between, say, efficiency and stability, weak NV freeness and stability, and also finally an incompatibility between weak strategy proofness, stability, and constrained efficiency. So just to recap, each of these stability concepts gives rise to a corresponding algorithm that is achieved by just applying VER with respect to that particular feasibility constraints corresponding to the stability concept. And all of these 4 algorithms, which are captured in this SVER, the first column, they fare quite well in comparison to some standard and very well-established algorithms, both for deterministic allocation and also for probabilistic allocation. I'd like to mention here that apart from stable matching and also allocation problems, the VER approach can be applied to problems way beyond allocation problems. It can apply to probabilistic voting, participatory budgeting, random allocation with bundles, and also 2-sided matching. And one nice contribution of, or I'd say one contribution of our paper is that VER provides a unifying theme, and it simultaneously generalizes many well-established and well-known algorithms in the literature. For example, based on what constraints are imposed, it captures serial dictatorship, probabilistic serial mechanism, and so on. And all of this is captured in this table, which shows that it simultaneously generalizes various algorithms in the literature. So just to conclude, we presented a robust preference aggregation rule that applies to any closed set of feasibility constraints. It especially satisfies nice fairness concepts when the set of feasibility constraints is convex. And as a case study, we showed that VER, when applied to constraints capturing stability concepts, it leads to stable matching rules, or desirable stable matching rules. With this, I thank you for your attention.